Take it up, that's 2 sections out of 6, so we got 4 more sections to go. Goals of the atmospheric measurement, by now you should kind of have pretty clear ideas. I need to know what the atmospheric parameters are in terms of an aerosol amount, an aerosol size, any column absorbers. How often we do these measurements, though, depend upon the type of conditions. If it's cloudy or if there's wind-blown dust, you're going to have to go a lot more frequently. If you're making measurements in a place where you have a land sea breeze, and it can shift during the day, you've got to take measurements a little more frequently. So a lot of it also depends on, do you have automated instruments or manual instruments? If I have a microtops, I'm not going to collect 500 optical thickness measurements. If I have an automated radiometer from the University of Arizona, 500 measurements is no problem. So this is all has to do with in terms of how we're going to do our collections. So basically the idea is that we're going to collect high frequency around the time when the temporal events warrant it, and we'll collect low frequency every other time. So if we're doing a Langley method, early in the morning I'm going to collect data really fast, because I want to take advantage of the sun angle changes. And then I can take data infrequently until I get to where I have an overpass, and I want to take data really frequently again, because I want to know what's happening right around the time of overpass. And a lot of this you have to do manually, and then you have the risk that you push the wrong button and things get cleared, and so there's a risk to that, but it also is, it keeps your instrumentation from getting too worn out, especially with a tracking mount or something like that, or if you just don't want to end up with too much data, which can happen, trust me. But we would get to where we would increase the sampling to 30 seconds about 15 minutes prior to the overpass and 15 minutes after. And that also allowed us to know what was happening as we were making measurements of the surface reflectance. So there was an advantage to sampling the atmosphere more frequently for the reflectance data as well. So here's all sky photograph data every minute. So overpass was, I think, at 1746. So you have 45, 44, 45, 46, 47. And you can tell it's automated. You can see some people walking in front. But when you start to see these types of clouds and they're moving around, then you start to wonder, you know, okay, when I see this picture here at overpass, there's enough of a little feature there that I'm not confident this is the perfect day. So I want to look at some of the other data sets to find out. But if I'm only taking data every 2 minutes, I take it at 45 or 47, I may be more confident that there's no clouds. So, you know, the frequency is what kind of storage do you have, what kind of camera do you have. What's nice is I can take this and start comparing now. This is at 1645, 1 hour later, 1725, this is in between those two, and then 1750, shortly after 1745, you have the pictures to go with the data. This is aerosol optical depth. So if I have clouds, what should happen to my optical thickness? Should it go up or down? Up. Very good. So if the optical thickness goes up, I have better confidence that even though it's pretty bright here, you can sort of see this cloud steadily extend. There's a bit of it here and a bit of it there. But where there's low optical thickness, there's no clouds. And it's, you know, it's really fun when you go back and you pick up the times. Here there's a little bit of a cloud. Here, what's nice is this was overcast. So we have, in terms of the measurements, which is really what we want to know, the quantitative data show there's no clouds. I still have some diffuse light issues that I might have to be worried about. But for the most part, and what's really nice is this also tells me, I was looking vertically down for Landsat, so in the center of that photo there's no clouds either. But I really want to go to the line of sight radiometer to know for certain what's happening there. So angstrom, Junge parameter. So this again is related to the particle size. Large particles, low angstrom, low Junge parameter. Small particles, large values. So when I go to a low value, and clouds tend to be large particles, so when I have clouds, which related to the high optical thickness, this also gives me confidence that it's a cloud because my angstrom, my Junge parameter, took a nosedive. I went from a typical dust situation to now I have ice particles, which are much larger. So again, now everything visually matches, and it's all together. I could have just looked at the angstrom and said, okay, well, overpass, it's variable, but at least I have this section here. If I average this part instead of that part, I have a valid data point that I can work with. So we take 10-minute averages, but this would be a case where I wouldn't want to go minus 5 minutes plus 5 minutes because I'm going to move into a cloudy situation. I'm going to go maybe minus 8 minutes plus 2 minutes. So up here, clear sky. Here, a little bit of clouds. The angstrom is still lower than what it was, but it's not quite as bad as in some of these other places. And then clear sky, another value. And what's nice is the angstrom, the Juncker parameter between the clear sky conditions pretty much look the same. So even though I have cirrus clouds moving around, I have to worry about these things. The background conditions are pretty stable. So then the inversion results end up pretty good from that day because I can go to a portion of the data set where I'm not affected by all these other things because of the way I collected my measurement approach. And I can basically now get into a retrieval where I have my water vapor, my ozone, my optical thickness at a reference wavelength, and my angstrom coefficient. And all of that is what I need for the rate of transfer calculations. And just some more examples, because again, I like the photos and I love comparing them. Another day, and we have a wonderful number of these sets. This is again the same condition, 1725, 1745, and then later on it got really cloudy in 1800. This is the downwelling irradiance, and this is the broadband downwelling irradiance. So you can start to see where the clouds are coming in. At the horizon, they show up in basically the irradiance measurement. You can see that variability. And at overpass, you can see that it looks pretty good. And then afterwards, again, you have all these clouds rolling in. You have all the clouds over there showing up, and you have the thick clouds here. So everything fits with the message. The line of sight radiometer data, as I mentioned, should get larger when you have clouds, because again, you're basically looking at black sky in this case. Here we have a little bit of cloud directly overhead. Here we have no cloud, so basically no cloud, some clouds, some clouds. But again, by the time you get to where the overpass was, we're probably not in bad shape. So in terms of the approach, this one goes pretty quickly because for the high reflectance, the goal is basically to get the best estimate for the day. You know, it's not, we don't have to be perfect. We're not atmospheric scientists making measurements. We're remote sensing people trying to do calibration with the reflectance-based method. Was today much different than we usually see? Is it really cloudy? Is it really hazy? Is it really smoky? How much is it changing during that time period? Is it clear now, cloudy later? Was it clear but it was kind of hazy? Did something happen during that time period that we need to take into account from a temporal standpoint? That's the measurement approach we need. This is going to be a lot different than when we start talking about reflectance. Because reflectance, we're going to have some, this is what you have to do. But atmospheric, we can get away with a lot of things because the atmosphere is not that big of a player in this discussion. As much as everyone will tell you otherwise. You'll leave this room and everybody will tell you, oh no, the reason vicarious method doesn't work is because you have the atmosphere. It's not the big problem. Spatial heterogeneity, what's the view like? And this is really the big one. If I look up where the satellite is, I look over where the sun is, are they both clear? Yes? We're good. We can get an answer that's probably going to be within 10% without knowing anything else. And then if I take a look at some of the other data, we can start making that uncertainty go down and down. The other way to look at it is, are the measurements I'm making today giving me an indication that I'm going to have larger errors than what I expect? That's the key. So if today looks hazy, but this is the way we always did our calibrations, that still would not be a major problem. My error budget would be valid. If I'm at Railroad Valley and I see smoke and cirrus, I I could probably get a good answer. I could get a result that might match, but I would have no confidence in my error budget. This is the key result. I would have no confidence in my error budget because that date doesn't match the assumptions I made in developing the error budget I have. I could develop a new one for that particular date, but you just have to understand that. You can go through that process, or you can just realize that you have larger uncertainties and say, man, my uncertainties are just really big today. Here's an answer, but I would not trust them. I have one from 3 weeks ago. Use that data point instead. Much different than if you were talking to me and I was giving a talk on atmospheric sciences. Right? This is what we call it fit for purpose, best practice, better practice, or good enough practice, or whatever the term is. We got into a discussion that some people refuse to use the term best practice because that means you can never improve it. English is sometimes, I think, is not a very good language. That got a laugh. That's how I remember that.